Okay, our final part, we're going to be able to use this composition to be able to determine if two functions are inverses. Of course, we can solve the functions and tell if they're inverses without doing function composition, but this is a neat little trick that we've learned over some years ago that can kind of help us figure out if two functions are inverses that sometimes can save us a little bit of time. So let's start with the one we just ended with. On a graph, inverse functions have a special property. So if I did the square root of x, and in y2, press y equals and put these in with me so you can see as we go along. If I do x squared in y2, and if I hit graph, there is a relationship between these two functions. Now I want to ignore this part here because you can square a negative, but you cannot square root negative numbers. So you notice this graph kind of cuts off here at 0 because in the domain are the x values, we're not allowed to input negatives in here and get real numbers. So I'm going to take my window and I'm going to start my window at 0 for x. And I'll start my window at 0 for y. We're just going to focus on quadrant 1. I don't know if you can tell, but there is a pretty cool relationship between the square root of x, which is the one here in blue, and x squared, at least in the positive quadrant, and that is they're both essentially reflecting over a diagonal line. Okay, if I drew a line straight in the middle, that line would indicate that they are reflecting over that line. That line happens to be x. Go to your y equals and put an x in there and press graph. Anytime two functions are inverses, that value x is going to be considered the line of reflection. Okay, so the reason is because when you do composition of it, when you put this function into that function, it becomes x. So our trick is, anytime we do composition of functions, whether we do it f of g of x or g of f of x, if we put them together and we end up getting x for both of them, and we really only have to do it with one, but we get x for both of them, they end up being inverses of each other. So let's try that right here. These we'll just stick with linear functions. So I want to know, are these two functions inverses of each other? Well, what we can do is, instead of actually solving for the inverse, we can say, well, let's try f of g of x. All right, so now what I'm going to do is I'm going to take my g of x and I'm going to plug it in for this x here. So that's going to be equal to f of x minus 4 over 3. And that way we're going to substitute x minus 4 over 3 into the x for here. So that x will get replaced with x minus 4 over 3. And if I work these out, I'm going to end up, these 3's are going to cancel out. So I have x minus 4, but then I have another minus 4. And those aren't opposites of each other. So that's actually going to give us x minus 8. So since that's not x, these guys are not inverses. And your answer is essentially no, okay? Here's your explanation. Since they are not equal to x, they are not inverses. I want you to do another graph of this. So what we're going to do is we're going to plug in, I'm going to show you why graphically they don't work either. I want to make my window normal again, so I'm going to make my negatives. And for my min, so I'll do negative 10 for x min and negative 10 for y min. That's the window button, and you can just change your window settings. So I'm going to go in and put these two functions. I'll leave the x, well, let me take the x out for a second. So if I put 3x minus 4 into y1, and if I put, I'm going to use my fraction menu, alpha y equals x minus 4 over 3 into y2, and if I press graph, take a second for them to load, this is going to be the 3x minus 4, and here's your x minus 4 over 3. Now they do look like they're reflections of each other, however, they don't reflect at this, they reflect at x minus 8. So what happens is if I put an x in there, that x is not split, okay? You want the line to be here to split it, not somewhere randomly up here. So graphically, that can explain why they're not inverses as well. Let's do the same thing for the bottom. So for part H, I want to do f of g of x, see if they're inverses of each other. So I will plug in that 2x minus 7 in for the x there. And so that's going to be f of 2x minus 7, which is equal to, I'm going to rewrite this and replace the x with this 2x minus 7. And if you simplify that, look at the 2x minus 7 and the plus 7. Now we got stuff to cancel out. Negative 7 and 7 cancel. So what I'm left with is 2x over 2. Since those 2's cancel out, you're left with x. That's indicating that they're inverses of each other. So since that's equal to x, since f of g of x is equal to x, they are inverses. And I do want to show you this on the graph as well. So I'm going to leave the x in for the third option, but I want to go to y1 and y2, and I want to input these two functions. I'm going to do my alpha trace, or alpha y equals. We'll do x plus 7 over 2, and then y2 would be 2x minus 7. Press graph. Watch them graph. This is going to be x plus 7 over 2 coming up first. Here's the 2x minus 7, and notice that that diagonal line is splitting it in half. Okay, that's what we want. That's your x value. That's your line of reflection. And here's your graphing proof. Here's your algebraic proof using composition. So try 13 through 17 using that process. You can check it in your graphs too if you want to double check, just to see if they are inverses of each other. And it's going to be either yes or no. Okay, your answer is not what you get. Your answer is a yes or no, but you gotta go through that process to get it. Hopefully that helps, and you can check your answers with me in class if you need to. Thank you.